So analyzing an IR spectrum, the first thing we'll need to know is the important IR stretching frequencies, and this is most of them. We're not going to be using these. We are going to pretty much ignore everything below 1500. Now, this is an example from your book. We have a compound. They've given us the molecular formula of it, and they've given us the IR spectrum. So the first thing we generally do is draw a line at the 1500 mark, and we say that this is the fingerprint region. We are not going to use it. Okay? Then we want to look for double bonds. We'll look for double bonds between 16 and 1800 in this region right here. We find one at 1650. This is going to be a carbon-carbon double bond, and we know that because of where its location and because it's not as strong as this, which is our carbon-oxygen bond at 1720. Next thing we want to do is, as best we can, draw a line at the 3000. We know that anything to the right of the 3000 is an sp3 hybridized carbon attached to a hydrogen, but on the left side will be an sp2 hybridized carbon attached to a hydrogen. So this one is got a double bond. Got a carbon double bonded to another carbon, and we have a hydrogen attached to it. That's what we're looking at. Actually, two hydrogens there. Okay, so what's going to be our structure? There are two structures that we could draw. It's going to have a double bond. It's going to need 6 carbons and 10 hydrogens and an oxygen. And we come up with these two structures as being possible. We know, however, that if our ketone had been conjugated the way this one is, this compound is conjugated with this, we could get another structure here. That we would have expected the ketone to absorb at a lower frequency at 1680 instead of our 1720. So this is the correct structure. So let's match each compound to its spectrum. So these can be challenging. You might want to turn off the video and look at them before you listen to me talk about them. Okay, so we ignore pretty much everything. Ignore everything to the right of that line. We've got something here that might be interesting, and if we look here, we've got carbon sp3 hybridized hydrogens there and sp2 hybridized. So I think we probably have a double bond. I think this is a carbon-carbon double bond. There is no ketone, so we know it's not this one or this one. So I would vote for that compound right here. So let's look at the one below it. I see I've got a very strong absorption right here, right around 1720. I don't know exactly that it's at 1720, but that sure looks like it's going to be a carbon-oxygen bond. If we do this. I don't see anything to the left of my green dotted line, so I'm going to assume that we're not going to have any double bonds. And we have two possibilities that have a ketone. We've got this ester over here, and we have this carboxylic acid. It's definitely not a carboxylic acid. If it was a carboxylic acid, I would expect a beard from about there to there. Well, maybe not quite that broad, but it'd be very broad. So it's not going to be the carboxylic acid, it's going to be the ester. Okay, let's do, we'll go do this one next. And I'm going to change colors again. We've got this peak here, which is kind of broad, not quite broad enough to be a carboxylic acid, but I think what we have here is an alcohol. We only have one thing with an alcohol, so it's going to be, that's what it's going to be. You can double check. We don't have anything that looks like a double bond. We don't have anything that looks like a triple bond. We don't have anything else interesting. So that's an alcohol. This one, the next one here, has this broad, this is the hydroxy that's on a carboxylic acid. It's that long beard, and it also has the ketone on it. It's going to have this sword. It's very strong absorption right around 1720. And so this is going to be okay, and I'm going to have to move it up a little bit. And we lost our figures when I did that. Okay, so here we've got, these are below 15, so we're going to pretty much ignore them. This is right at 30. You can't see it. Let me move it up. There we go. This is right at the 3000. So there's nothing, no double bonds, no indication that we'd have a double bond there, no indication of an sp3 hybridization. So this is going to be a pentane. That was one of our choices. And that leaves this last one will have to be this amine. That's the only thing left. But let's look and see why we think it would be the amine. Well, we don't see any indication of double or triple bonds. We've got sp3, there's carbon there. We've got this interesting little hump right here with the two forks on it. It's not large enough to be the finger that we expect from a hydroxy group, but it's got two humps in it, and that makes it a primary amine. It's smaller than the hydroxy because it doesn't have as much of a dipole. We've got, with the hydroxy up here, we've got a fairly big dipole.